So continuing from question 8, we have a set of logarithms, so log base 8 of 6, log base 8 of 3, and log base 8 of 4. And I noticed that at the very end of the exam review, there are a set of log rules that you could use to help you here. And so basically it's going to be these two, rules 1 and 2. And I'm going to show them up here at the top. So if we look at what we have so far, if you have two logarithms of the same base, so we have log base 8 on all of them, so two logarithms of the same base that are being subtracted from one another, so this first two, the 6 and the 3 can be written as a quotient, or you dividing the two of them. So I'm going to show that first. So these first two can be written as log base 8 of 6, and then we're subtracting by 3, so we're going to do divided by 3. And this is just going to be 6 divided by 3, that's just 2. So we're going to write these first two boil down to just log base 8 of 2. And then right beside we have the log base 8 of 4. So the next step here would be using the second rule that was just below at the very end, so you could reference it during your exam, which is that when you have two logarithms of the same base that are added together, what you get here, so we have log base 8 of 2 plus log base 8 of 4. What you get here as the product is going to be whatever you have on the inside, so the 2 and the 4 that are multiplied together. So you get log base 8 of 8. And this would be your answer. However, if you get 8 and 8, anytime that you get any actual logarithm, so log base anything, so it could be like 4 of 4, just as a reminder of what the logarithm is, it's saying 4 to what power is going to give you 4, or 8 to what power is going to give you 8. And the answer in all of these cases, if you have the same thing inside here as your base, is always going to be 1. So your final answer is going to be log base 8 of 8, which is equal to 1. So that's what we get here. Question 8. So I'll write that here, log base 8 of 8, which equals to 1. Question 9 asks for the inverse of the function f of x equals 5 to the x power, 5 to the x power. And so to find the inverse of a function, what you do is you swap your x and your y, where your y would just be like your f of x. So I'm going to write this here as like y equals f of x, and then we have to swap them. So I'm going to make the swap, and then I'll say x will be equal to 5 to the power of y. And our inverse is whenever we've isolated y on its own. So right now, y is in the exponent here, and I need to get rid of it. So what you could do, the opposite of an exponent is a logarithm. And so that's what we're going to use in order to get this y that's in the exponent and bring it down. So because we have a 5 here, it will be useful to use, because we could choose really any logarithm we want, but I'm going to specifically choose log base 5. So I'm going to take logarithm base 5, and I'm going to do that on both sides. So I'll do log base 5 of x be equal to log base 5 of what I had on the right, so the 5 to the y power. And so for the logarithm rules, if you have anything, the log of anything that has an exponent, this exponent that we have here, this y, can be brought to the front. So I'm going to write this as y times logarithm base 5 of 5. And then you'll notice here, this is log base 5 of 5. This is just like we were talking about over here. If you have any base or logarithm whose base is here, and it's the same thing that's on the inside here, it's always going to be equal to 1. So I have here log base 5 of 5. Or in other words, 5 to what power gives you 5? The answer to this is just 1. So our final answer would be, our left-hand side is log base 5 of x equals y times 1, or just y. And so now that we've isolated y on its own, this is our inverse. So our inverse function is log base 5 of x. So there we go. We write that up. We just got rid of some space, and then we can go on to question 10. It asks us to solve for logarithm base 4 of x plus 3, which equals to 2. And so if we're solving this, we're basically being asked to solve for x. So here I need to find x on its own, but right now we have this logarithm. And so to get rid of this logarithm, we're going to do the opposite of a logarithm, which is called the exponent. And the exponent that I'm going to choose is the exponent of 4, because we have 4 here. So it's going to be useful to solve this equation. So I'll first take 4, and I'm going to raise everything to the power of log base 4 x plus 3. And I have to do that to the other side. So it's 4 to the power of 2. And on our left-hand side, here I have an exponent and a logarithm. So these are opposites of one another, and these end up canceling each other if their bases are the same. So here I have a base of 4, and I have a base of 4 here. So therefore, these are going to cancel each other out, and that will just leave me with whatever I have up here, which is the x plus 3. So therefore, my answer is going to be x plus 3 is equal to 4 squared. If you square 4, that'll give you 16. And so you can say x on its own has to be 16 minus 3, or 13. So that would be your answer. X equals 13 for 10. Question 11 is quite more theoretical, I guess, because it asks if g and f are inverses, then what will the result of g of f of x give? And it might be easier to think of it like this. If g and f of x are inverses, so g of x would be equal to the inverse of f of x, and then you also have f of x. And it asked, what happens when you do this? What happens when you do g of f of x? Or you could write it as the inverse of f of x. And what would happen here is that your inverse and your function are going to basically cancel each other out, we could say, and you'll just be left with x on its own. And that's actually the answer here. So it's supposed simply x. This next one is similar to the one that we had done up here, question 8. So question 12 asks to write these here as one single logarithm. And so we're going to use the log rules again. And so I'll write that out here. Log base 6 of x to the 5th power minus 2 times log base 6 of z. And it asks to write this just as one simple logarithm. And so we notice that we both have base 6 on both, so that's good. But we can't move forward so fast because we have this 2 kind of like in our way. And so there was an example, I don't know if I still have it, no, I've erased it right now, but one of the log rules is that if you have any log that has an exponent. So for example, I have x squared here. This exponent can be brought to the front, which means that if we have here, in this case, a 2 in the front of the logarithm base 6 of z, that came from up here. Or I can put that back and it would be still equivalent. So I'm going to do that as the first step. And we'll write this now as log base 6 of 5 to the, or x to the 5th power will be still the first term. And we subtract by logarithm base 6 of z squared. And now we have two logarithms of the same base, 6 and 6, that are being subtracted from one another. And if we're subtracting two logarithms, the result will be a single logarithm, so log base 6. But I'm going to take the first one, which would be x to the 5th power, and then if I'm subtracting it, I'm going to be dividing by whatever I have here, so we divided by x squared. And this will be our final answer. So my final answer is going to be log base 6, x to the 5th power divided by x to the 2nd power. 6 x to the 5th divided by z squared. Question 13 looks quite simple. Just asking to solve for x here, and we have an inequality, so all we have to do is isolate for x. So I can move the negative 2x term to the other side, which will give me 5 is greater than 7 plus 2x, and then move the 7 to the other side, which will then make this 5 minus 7 is greater than 2x, which would be negative 2 is greater than 2x. And then lastly, I'll divide both sides by 2. So I'll have negative 1 is greater than x. That's our final answer, and so I'm going to just write it here. Question 14. Jen walked around a circular track 1.5 times. Describe her movement in radians. So a circular track, you can imagine this is what she's walking around, and she's made 1.5 rotations. So a full rotation would be 360 degrees, and she's done another half rotation. So she's done, well, actually we can write this in, it asks for radians. So her walk was 2 pi, which is a full rotation, and then she does another half rotation. So plus half of the 2 pi would just be pi. So in radians, she's done a total of 3 pi radians that she walked. That's the angle, or the degree that she walked through. So in radians, this would be 3 pi. This one here is going to be using sign addition and subtraction laws, which I believe is written for you at the bottom. So I'm going to quickly reference that. There we go. So here, it's like compound angles, or when you have addition of some. So basically, we're given one of these here. I'm going to go back up and double check which one we should use, and then we're going to plug x and y into just a single sine or cosine. So if we go back up to our question that was start, we want the one that has sine, cosine, then plus cosine, sine. So we can just remember that, sine, cosine, plus cosine, sine. Here we are, sine, cosine, plus cosine, sine. That's the first one. So it says if we want to write this as a single angle, or sorry, a single term, we're going to use a sine of x plus y. And our x and y is going to be whatever was beside the sine and the cosine here. So we're going to go back up and say that the equivalent to this is just equal to sine of pi over 3, that was the first one, plus pi over 6. And it says do not evaluate, so you could leave it like this. An even simpler, or actually this may not have been actually what it was asking for. I think it was, but maybe it wasn't. So if it's asking for a single ratio, this isn't actually a ratio. I have a single term. But if it's asking for a ratio, then we have to use the cosine, or sorry, the special triangle. So I think this actually wasn't what it was asking for. So I'm going to quickly do this again and use the triangle that's also given at the bottom. But I noticed that on your sheet it's given as in degrees. So here's pi over 3, pi over 6, 1, square root of 3, and 2. And it's asking to just rewrite this. So this is still true, I guess, but I don't think that was the right question. So had it asked about a single term, you could use that. But if this is asking for a single ratio, I think it's asking you to rewrite each of these terms as to what their equivalent term is using special triangles. So we can use sine, or our special triangle to find sine of pi over 3. Here's our angle pi over 3. And I need to find sine of this angle. So sine is opposite over hypotenuse, and then cosine is adjacent over hypotenuse. So if we're asked for sine of pi over 3, that's opposite. So it's square root of 3 divided by the hypotenuse, 2. So there's our first part. And then times cosine of pi over 6. Here's pi over 6. And cosine is adjacent, so it's going to be here. Square root of 3 over the hypotenuse, that's 2. And so if we multiply these together, we'll get the square root of 3 over 2 times the square root of 3 over 2. And if you have two square roots that are multiplied by each other, that's just going to result in the number itself that's being square rooted. So that's going to be 3 on the top divided by 2 times 2 on the bottom, or 4. And then we're going to do the next term, which is cosine of pi over 6, sorry, pi over 3, and then sine of pi over 6. So cosine pi over 3, and then times sine of pi over 6, using the same triangle, and then finding what those values are. So cosine of pi over 3, here's pi over 3. Cosine is adjacent, so it's here, 1, over hypotenuse, 2. And then sine of pi over 6 is opposite, should also be 1, divided by the hypotenuse, also 2. So it's the same result again. And so we get 1/2 being multiplied by 1/2. So that ends up being 1/4. And so our final answer ends up being 3/4 plus 1/4. That's going to be 4/4 or just 1 as the final answer. So rewriting this as a single ratio, we can write it as 4 over 4 or 1. So there's our ratio. And then for the next one, for solving for x here, we notice that we have two bases that are not the same. So we have 2 as well as 8. And so this is going to be a bit trickier to start with. Like you can't immediately start and then solve this. So we have to do what's called a change of base. So you'd have to, if you're ever presented with something like this, you would have to think about like what what power could I change so that I'll get the same base? So for example, here if my base is 2, I could say, well, you might recall that 8 is actually 2 times 2 times 2, or 2 to the third power. And then if I could write 8 as a base of 2, then I'll have a base of 2 on the left side and on the right side, and then it's going to be easy to solve this. And we can go forward with like logarithm rules and stuff to solve this. So that's our first step, is I'm going to write 8 as 2 to the third power, and I'll do that just here, I guess. So we have 2 to the power of 2x, which would be equal to 2 to the third power is going to replace 8. That's all being still raised to x minus 1, so I have to input an x minus 1 up here. And then this 3 and the x minus 1, this is called the power of a power rule. So these are being multiplied together, so this ends up being 2 to the 3x minus 3. And so now it's a bit easier now, because we see that, like, well, if these are equal to each other, whatever their exponents are have to be the exact same. And then we can just say to ourselves that 2x has to be equal to the exponent here, 3x minus 3. And this now becomes just an algebra problem. So I have to move all of my x terms to one side. So I'll move these over here. And that will leave me with 3x minus 2x minus 3 equals 0. And then I'll move the 3 to the other side. So I'll get 3 is equal to, and then 3x's minus 2x's, which leaves me with 1x. So our final answer here is that x has to be equal to 3. So I'll write this here as x is 3. And I suppose even with this, you could double check your answer by like plugging it in and seeing if you have an x, and you plug it in there, and you plug it into here, they should be the exact same. The next one, what is the pH of a solution with a hydrogen concentration of this many moles per liter? So they're basically asking, okay, this is a bit of a tricky question. You could put this into your calculator and it should just spit out the answer, because if you do log, and if there's never any base shown here, then it's just base 10. So log base 10, and you put in 0.0001. This will just actually spit out a number. And if I do that, it would be negative 4. And then there's a negative at the front. So this is being negative 4 times a negative. So your answer will just end up being positive 4. Actually, not so bad, actually. And then for 8, or 18 rather, solving for x, if you have this equation here. And so you notice here that we have two terms that are being multiplied together, and on the left-hand side you have a 0, or two factors rather than being multiplied together. So you could ask yourself, like, how can I make this or this equal to 0? And the first case that this would be equal to 0 is if x plus 4 is equal to 0. And that's only true if we move 4 to the other side. X is equal to negative 4. So there's one solution. Another solution is if the other factor was 0, because anything times 0 is going to be 0. So you could basically say, well, if we let x minus 1 equal 0, I move the 1 to the other side, x has to be equal to 1. So that's my other solution. we have an x in the denominator, which isn't going to change our answer, but we could probably also say that x should not be equal to 0, because if any case where we divide by 0, you get some error. So this is a restriction. It's not really asking for it, but I think that it might be useful to write, just demonstrate to your teacher that this is also to be avoided. So that's that point. So this next part, I'll show both of these answers here. So it says to state the quotient and the remainder and then show your division. So the quotient would be, we're dividing this larger polynomial by this smaller polynomial, and your quotient is going to be whatever your result is. So I'm going to be dividing it x cubed minus 10x squared plus 3x plus 6. And it's important to remember that these have to be in the correct order. So it has to be the highest degree to the lowest degree. And I should be always going down by 1 or leaving a space if they're not showing that. And they do that in this level 3, 4. So I'll show that in the second example. But for the meantime, we'll go through this one together. So for the polynomial long division, you're always asking yourself, how do I get rid of this leading term? So the leading term in this first case is going to be x to the third power. And we're going to get rid of it by finding or asking myself, what times x will give me x cubed? And that would be x squared. So I'm going to put an x squared on top of this x squared that I have here. So x squared. And then I'm doing x squared times the terms that I have on my left here. So x squared times x, that's going to be x cubed. And then x squared times 2 will be positive 2x squared. And then the next step is to subtract what we have. So I'm subtracting everything we just got from the top row. And so that will leave me with x cubed minus x cubed, 0. That's negative 10x squared. And then minus 2x will be minus 12x squared. And then next step is to pull down the 3x. And the next question now we're asking ourselves is, again, how do I get rid of this leading term, which is negative 12x squared? So if I were to get rid of it, I need to find it or figure out, like, what do I have to multiply to the x that's out here so that I get a negative 12x squared. And right now, if I have an x, what's missing is a negative 12x. And I put that on top of this x column that we have here. So negative 12x times x, that's giving me what I want, negative 12x squared. And negative 12x times 2 will give me negative 24x. And we subtract the 2. I have negative 12x, and we could expand this to make it clearer if you want. This becomes positive, and this also becomes positive. So negative 12x plus 12x, it's going to be 0x squared. And then we have 3x plus 24x will be positive 27x. Then we have the last step of pulling down the 6 plus 6. And then this has to be a 27 that I'm missing, because 27 times x gives me 27x. And then 27 times 2 would be 54. And then 54 will go here. We subtract the 2. So I have 27x minus 27x, that's going to be 0. And we have x minus 54, 6 minus 54. So this ends up being negative 48. So a remainder, well, this is our quotient we get up here. And that asks also for the remainder. So we get x squared minus 12x plus 27 and then you put a remainder of negative 48, and we divide by whatever we were dividing this entire polynomial by. So it's x plus 2. So that's our result. And so in the second example, there is a slight, increase, right, in the difficulty, because the setup's only slightly different. But this is similar to what we've done in an earlier part of the video, or in part 1. So I'm going to set it up. Plotting this, and we have 6x cubed. And we notice there's no x squared term here, so we have to accommodate for that and do plus 0 x squared. And then we have an x term, so we're going to minus 10x, and we have the constant. So again, it's always going down. So we have degree 3, degree 2, degree 1, and then a constant. And if you don't put these zeros, it's going to make the long division harder, or you'll make an error. So same sort of idea. What we're looking for is, how do I get rid of this leading term? So I need to get, I already have a 2, so I have to be aware of that. So 2 times 3 will give me a 6, so I'm going to have a 3, and I need it to be degree 3. Right now I have only degree 1 here, so I need to add 2 more degrees, so I'm going to have to put 3x squared on the top, and then 3x squared times 2x will give me 6x cubed. And I do the same with the next term. 3x squared times negative 3 is negative 9x squared, and then I subtract these two. And it's the same algorithm, the same steps each time. So these get subtracted, this gives me 0, and then a negative times a negative will be plus 9x squared. So I get positive 9x squared. And then I draw this down, negative 10x. And then to get this 9x squared removed, I need to get something times 2 will give me a 9, so 4.5. So I can do 4.5x. And then 4.5x times 2 give me 9x, and then times x give me 9x squared. So I get my 9x squared, and I'm going to subtract it by 4.5 times 3 will give me 13.5. So minus 13.5x. And these are being subtracted from one another again. So positive 9x, and I can have minus 9x will be 0, x squared. And then we have negative 10x, and then a negative times a negative will be plus 13.5x, which will leave me with plus 3.5x. And then, like before, take down the last part. And then this last one, we're asking ourselves, what number times 2x will give me 3.5x? So this is another fraction, so I need to have some number. When I multiply it times 2, will give me 3.5. And so this number that I want to find, I'll just call it n, would be, I could solve for it by dividing both sides here by 2. So this will be some sort of fraction here. So if we do 3.5 divided by 2, we get 1.75. And so that's the last number that I'm looking for, so that I can get rid of the 3.5x, getting rid of that leading term again. So 1.75 times 2 gives us 3.5x, and then 1.75 times 3 is 5.25. And just like before, you subtract all of this. So you can expand this again, the negative There's no negative there. Yeah. So we expand this, so we have 3.5x minus 3.5x will be 0x. And you have negative 6, and then two negatives here will make a positive 5.25. So you're left with minus 0.75. So that's going to be your remainder, and just like the last time, we'll write our quotient as what we got on the top, 3x squared plus 4.5x plus 1.75, and then we have our remainder here, which is negative 0.75 divided by whatever we're dividing by at the start. So it's going to be 2x minus 3, and that's your final answer. So the added difficulty in this one was the setup. So noticing that you have to leave a spot here for the x squared. And also we had a lot of decimals that were included in this one, which made it a little bit trickier, but still the same steps. Okay, on the next one here, you're asked to factor completely. So I'll start this one here. I'm moving all of the terms to one side. So I get x cubed minus 3x squared minus 4x plus 12 equals 0. And this is what we're looking for here is a way so that I could find an x such that this whole thing becomes 0. That's like the goal of factoring this. And it's a degree 3. So anytime it's bigger than a quadratic, the goal here is to solve these by polynomial division. So it's going to be more like this. But we're not given an explicit thing that we have to divide this by. We're just trying to find this factor by guessing. So I could say, let's try x equals to -1, for example. And then this first term will become -1. Then we have -3 times -1 squared is just 1. -1 times, and then with -4 times -1 plus 12 equals 0. So this becomes -1 minus 3 minus, no, -1 minus 3 is -4. And these two becomes plus 4, sorry, plus 12. And that's not going to be equal to 0. So that didn't work. So then you would try something else. So we could try, what if x is equal to 1? So if x is equal to 1, we would get 1 for the first term, minus 3, and then x squared will just be still 1, minus 4 times 1 plus 12 equals 0, gives 1 minus 3 minus 4 plus 12. That's still not going to be equal to 0. And then you just keep going, trying a different number. So maybe -2. -2 cubed would be -8. And then we have minus 3 times -2 squared minus 4 times -2 plus 12 equals 0. So -8, -3, -2 squared is going to be 4 times -3 would be -12. And here we have plus 8 plus 12. You see 8s will cancel out, the 12s will cancel out. This does equal 0. That means that -2 was the factor of the original equation that we have up here. So let's work with that. We could say that I could divide this original fraction that we have here, or the original function, let's say, by x plus 2. And this x plus 2 is saying that if I let x equal to -2, it will be -2 plus 2, that's going to be 0, because we saw that this is a factor of this whole thing, or it causes this whole thing to become 0. So that's why it's written as plus here. So we're dividing this whole thing as you've done before. So I'm going to have to find something that gets rid of the x cubed, which would be x squared. X squared times x cubed would be, or x squared times x would be x cubed. X squared times 2 would be positive 2x squared. You subtract the 2. These first two terms are going to cancel out, and you'll have, for the second term, negative 3x squared minus 2x squared will be negative 5x squared. And then I need to get rid of this, pull this down. So I need to have negative 5x, because negative 5x, when you multiply it by x, gives you negative 5x squared. And then we're doing the same thing as we did before. Negative 5x times 2 is going to be negative 10x. Subtract this, you could expand that so that it becomes negative 5x squared plus 5x squared plus 10x. So we have these cancel out, 0. Negative 4x plus 10x gives me 6x, and then plus 12. After this, we get 6, because 6 times x will give me 6x, and that will cancel out. And then 6 times 2 gives me 12. So here in this one, we get 0 for our remainder. We get no remainder. It's perfect. That's just confirmation that we found a factor. So we can now write this whole thing that we'd started with as the factor that we found, which is x plus 2, times the quotient that we got up here. So this is x squared minus 5x plus 6. And now we have to factor this if you can, and in this case I believe we can. So I'm looking for two numbers that are going to sum or add up to negative 5. And those same two numbers, when I multiply them, will give me 6 here, or 1 is the coefficient of their first term times 6. So this is your b value. I'll just write b here. And this is going to be always equal to your a value times c. So our a here is 1, which is the coefficient of the x squared term. And then our c here is positive 6, so it's a times c is 1 times 6, or just 6. So I'm looking for two numbers that add up to negative 5, and when they are multiplied together give me 6, and that would be negative 2 and negative 3. So we're going to have to factor this, so we need more space. Let's do that over here. This term will split the middle term. So you have x squared, and instead of writing the negative 5, we found that we could use negative 2 and negative 3. So we're going to do that. Negative 2x minus 3x plus 6. So we just changed that. And now we can factor both the first and second part here. So these first parts will be done, or I could factor the first part by doing removing an x, and then I'll be left with x minus 2. And then in the second group here, I could take out a negative 3. And if I take out the negative 3, I'm left with x minus 2. And so our final answer here in factoring this quadratic would be x minus 2 and x minus 3. So the final answer for the first part. So for final answer here, we would get this first part I'm highlighting. That's the first one that we found by guessing. So the first factor was x plus 2. The second factor will be x minus 2. And the last factor is x minus 3. So that's the factored form, or the totally factored form of what we have up here. So I'll just write that. And then ask specifically for the solution. So it's not actually necessarily just to factor it, but to solve by factoring completely. So that was like 9% of the work. And so now we just find what these solutions are. So what's basically the values that makes this factored form 0? And we did that already for one of them. We said x has to be -2 up here. So that's one of our solutions. So x equals to -2. And then for the second one here, I'm asking like, what does x need to be to make this second factor 0? And it has to be a 2, because 2 minus 2 will give us 0 here for that middle term, or for the middle factor. So that's a second solution. And then the third solution here will be x has to be equal to 3, because if we have 3 minus 3, we also get 0. So those are the three ways in which we can make our function here equal to 0. So it's -2, 2, and 3. So those are our three solutions. Same thing is true for this level 3-4 one. It's just got an extra term, and they've already moved everything to one side for us, so it's a little bit simpler in that sense. But all the steps are still the same. So I'm going to do this one just by clearing the space. So you can try and guess again. What is the number for x that will make this whole thing equal to 0? So I'm just going to try -1. So I'd always advise doing like -1, 1, -2, 2, or even up to like a half or -1/2. Like these are probably all the ones that you're going to try, and then one of these will work. Yeah, like it's sort of like always the case that it's one of those. Maybe you have to try something else, but generally those are like the answers. So I'm going to just try -1, see if that works. So if we let x equal to -1, I'm going to get 4, -1 to the 4th power plus 4, -1 cubed plus 5, -1 squared plus 4 times -1 plus 1, and see if that's going to be equal to 0. So the first one we get 4. -1 to the 3rd power is going to make -1, so we need -4. -1 squared is going to be +1, so we get +5. Here is going to be -4 plus 1. So those cancel out, but this one doesn't quite cancel out. So we're close, but it didn't work. So I can try, I'm going to try -2. The reason why I'm also trying -2 and why I tried -1 is that I see a lot of this is plus, plus, plus. And so if all these are plus, like no way could this be 0 unless one of them is negative. So that's why I'm trying that. So if we try that, 4 times -2 to the 4th power. That's equal to my calculator. To the 4th power. This will be 16 times 4 will be 64 for the first term. Plus -8 is -2 cubed. So -8 times 4 gives me -32. And then I have to add 5 times 2 squared is 4. So it's going to be 20 minus 8 plus 1. I don't think this is going to work either. Yeah, it's going to be too big. I'll try another negative number now. I'm going to try negative a half, as I mentioned before. So, or 0.5. 0.5, negative 0.5 to the fourth power times 4 gives me a quarter, 0.25, plus 0.5 cubed times 4, negative a half, 5 times 5 divided by a quarter, plus 1.25, gives me negative 2 plus 1. So maybe this will work. So if I add all of this up, 5 plus 1 minus 2, there we go. So this works. So one of our solutions is x is equal to negative a half. So if x equals to negative a half is one of the solutions to give us 0, we can move this back basically and say that x plus a half is one of my factors. And we continue now doing polynomial division. And so this is going to be quite long. So I'm going to just kind of write out the steps. I hope it all goes well. Steps are still all the same. So x plus a half is now dividing what we started with. So 4x to the fourth power plus 4x to the third power plus 5x squared plus 4x plus 1. So I need to get 4x cubed here times x will be 4x to the fourth power, and then 4x cubed times a half will be 2x cubed. Subtract them, that's going to be 0 here. 4 minus 2 gives me 2x cubed plus 5x squared. And for the next term, I need to get rid of the 2, so I do plus 2x squared. 2x squared times x gives me the 2x cubed that I wanted. And then 2x squared times a half will just be x squared. Subtract them, that's a 0. 5x squared minus 1 gives me 4x squared. Taking down the next one of 4x. And then I need plus 4x times x will give me 4x squared. 4x times a half gives me 2x. 0, that's 2x. Now I need to find the last one, which is going to be 2, because 2 times x gives me 2x. 2 times a half is just 1, and we should get 0. So we know we did it right because we have a remainder of 0. So that confirms that this that I'm highlighting here was a factor, because we shouldn't have any remainder. So that means our quotient here, which we got on the top, is what we now have to find another solution for. So I'm going to write x plus a half. That's one of our factors of the very large fourth degree quartic. And we just do the same steps. So I'm going to replace everything here, what we have here, and now find a solution to this function. Get rid of everything else. So we're going to try. I notice everything's positive again. I have something positive plus another positive. So it's going to be useful to try something negative so that this ends up becoming 0. So I'm going to try x equals negative 1. So 4, negative 1 cubed, plus 2, negative 1 squared, plus 4 times negative 1 plus 2. This first one's going to be negative 4, plus 2, minus 4, plus 2 is not equal to 0. So I have to try again. I'm going to try 2. Sorry, negative 2. Negative 2, negative 2. Negative 2 cubed will be 8, negative 8. And then times 4 will be negative 32. Plus 2 squared is 4 times 2. 4 times 2 is 8. Plus 8. Sorry. Negative 8 here. Plus 2. So that's again not equal to 2. So maybe we have to try another. We could try 3. Negative 3 rather. Or it could otherwise be maybe it was another half. So I'm going to try 3 first, negative 3. So 3 cubed is 27. I think 27 times 4, 108. Negative 108. 9 times 2, 18. And this will be much too large with negative 12 plus 2. It's still not 0. Let's try negative a half. So another half here. Negative a half, negative a half, negative a half. And hope this works. So 4 times 0.5 cubed, or negative 0.5 cubed, will give negative 0.5. And then 0.5 squared, or negative 0.5 squared times 2 is positive 0.5. And then negative half times 4 gives negative 2 plus 2. And so we found it again. So that means that x plus a half was another factor of this. So right now we got 2 in a row. So 2 of the same in a row rather. So in the end we're going to write that the factor was x plus a half squared. And now we have to do the polynomial division for this one. So this is what we have, and we know that one of the factors is a half. So same idea we did before. It's quite long, so it's long, but the steps are all the same. So that's anything. I'm missing a square here. Okay, so same steps. You need to have here 4x squared, which can be 4x cubed, and then 4 times a half will be plus 2x squared. And then subtract the 2, it's going to be 0, 0. I get 4x. And to get rid of 4x, I just need a 4. Hold on. Yeah, okay. I think it would be better to just write this first. We get 0x squared. And then you can ask yourself, how do I get 0x squared cancel out? I'm going to just need a 0 here. So I'm going to do plus 0x. 0x times 0 times x, so it's going to be 0x squared. And then anything times 0 will just give me 0x there. So I get 0, I get 4, x, and then plus 2. And then now I'm asking myself, just because I don't want to break the rhythm of having x squared, and then we have an x term, and then we have a constant term, I just want to show that that middle term will just be 0. And then here I need to have a 4, because 4, we'll cancel out the 4 down here. And then 4 times a half will be 2, and again we get 0. So our last answer would be this. So right now we've got started up here with all of this, and found that this is equal to, and I'll write it down here, that's equal to x plus a half squared, because we found two factors that were x of a half, times what we have on the top here, 4x squared plus 4. And I just got rid of that middle 0x because it's a 0. But there's one final step, and that's factoring this. And this is called a sum of squares, so there's no formula for it. If it had been written as 4x squared minus 4, there's a special formula. I'm not sure if it's written and at the bottom here. You guys have these here. No, you guys don't have a difference of squares. So had it been a difference of squares, then we could have done a little bit more, but it isn't. Just showing that though, a difference of squares, you recall if you have something like a squared minus b squared, your answer would be a plus b and a minus b as the factored form. But because it's plus, we don't have to worry about it. I was just showing that here. But we do still have a common factor, and that's just the factor fully. So there's a 4 in the first and the last term, so I can factor that out. So our final factored form would be x squared plus 1, and then x plus a half squared. And then we're asking ourselves now, well, what's the solution? How does this equal to 0? From here, you can test this factor and this factor to see which of these factors make the whole function, so all of this equals 0. And if you try the first one, you'll see that's impossible, because you have x squared plus 1. If you try and let that equal 0, you'll get, you can try and like move this to the other side, and you'll have x squared equals negative 1. And if you try to do the square root of negative 1, you're going to get an error. So this is impossible. So there's no solution from here, but from this one, if you want to see how this could be equal to 0, we could say let this x plus a half equals 0, and then moving this half to the other side, you'll see that x equals to negative a half. And that's your only solution that you can get here from these two factors. So our solution or solutions is just the one. It's just when the x is equal to negative a half.